In this video, I'll go through what you need to know about inverse functions. So typically every exam 1 and exam 2 has an inverse problem on it, and more often than not I find that they form the backbone of the more difficult problems. Now, for an inverse function to exist, the original function must be 1 to 1. So it has to pass the vertical and horizontal line tests. Now you might wonder why it has to be 1 to 1. Well, if we graph y equals x squared, which is that, and then think about the graph of x equals y squared, y equals plus or minus root x, what that is the top half of the root and the bottom half of the root. So there's the inverse. So this is the original and this is the inverse, but what you'll note is that the inverse is not an inverse function. So to make it an inverse function, it has to be 1 to 1, and that is that one of these parts, either the top half or the bottom half, needs to go so that it can be a function when it's inverted. So for example, with the parabola, we could invert it if we run a domain restriction on it by having only, say, this part, or only this part, or only this little part of the parabola. All of them are invertible because when you inverse them, you can see here that that one will just be an inverse that looks something like this, and we note that this is 1 to 1 as well. So the inverse function is created by swapping x and y, thus the domain and range of the original function and the inverse swap. So that's important to know. The result of swapping is a reflection along the line y equals x. Okay, so what happens is when you swap x and y, all the coordinates swap, and the result is that we get a reflection. So here is the original function, so it looks to be the y equals x take 2 all squared parabola, and it's only the values from the turning point to positive infinity. Now when I inverse it, so note that this coordinate here is 2, 0. When I swap x and y, this is the coordinate, so 0, 2. So that point there goes to that point there. And all the other points swap around. So what we get is this reflection along the line y equals x. And the really important observation is that if there is an intersection between the inverse and the original function, it'll always occur along the line y equals x. So see, this is where they intersect each other, and it's no accident that they intersect along the line y equals x. Okay, so hot tip, before inversing, write out the domain and range of the original function, because when we swap x and y, the result will be that the domain of the original will be the range of the inverse and vice versa. Alright, so let's start with a simple inverse of a linear. So the domain of f, the original function, is all reals. The range of the original function is all reals because this is the linear function that looks something like that. Okay, so what we'll do, let y equal 2x take 7, swap x and y, x equals 2y take 7, and then because they want the inverse function f negative 1 of x, I need to make y the subject, so it's x plus 7 on 2 equals y, and therefore my inverse f negative 1 of x is going to be x on 2 plus 7 on 2, or you can write it in that form, that's fine, where x is an element of all real numbers. Now, how do I know that that's the domain? Because the range of the original was, or will be, the domain of the inverse. Alright, next one. So we've got a parabola, and it goes up 3 units, and it's inverted. It's going to look like that. And it's true only from 1 to positive infinity. So here is 1. If we bang 1 into the function, we get -1 plus 3 is 2. Okay, so there's 2. So it's going to go like that. Now, that graph there, whilst not necessary, is important because we can say our domain is just 1 to positive infinity. There it is there. And our range is going to be, so we can see here it starts at negative infinity and goes all the way up to and including 2. Alright, so let's get on with it. Let y equal negative x squared plus 3, swap x and y, x equals negative y squared plus 3. Then we're going to do negative y squared equals x take 3, y squared equals 3 take x dividing by -1, y equals plus or minus root 3 take x. So what we've got here is the inverse of the full parabola, but now we need to think about what part is true for this inverse, because really that's just the square root function. It's moved across 3 units. Is it 3? Yeah, 3 units across, and then it flicks that way and that way. So that's the inverse, not the inverse function. So what we need to note is that we need to keep either the top half of the root or the bottom half of the root. Now, which one are we going to keep? Now, what I know is that the range of the inverse will be this, which is 1 to positive infinity, which means that we're going to take the top half here. So we're going to say this, but range of the inverse is, what was it, 1 to positive infinity? Is 1 to positive infinity. Therefore, y is equal to, so we'll keep the top half only, root 3 take x. So what we've done is dumped the negative solution. F -1 of x equals 3 take x, where x is an element. Now the domain of the inverse will be the range of the original, so it's going to be negative, try that again, negative infinity to 2. Alright, so anything that puts forward 2 solutions, you just need to vet one of the solutions by using kind of the picture of the graph and working out which one is going to go and which one's going to stay. Okay, here we've got a parabola again, and b is the smallest real number such that f has an inverse function, and find b and f -1. Alright, well first of all I think we should find b, so we'll do that by doing a quick sketch of this. x take 3, and that means that my intercepts are going to be 3 and 0, and it's an upright parabola. Alright, so I know for a fact that this needs to be 1 to 1. Alright, now how low do we need to go? So we need to start shaving this parabola off, and where we're going to shave it is at the turning point. So that's when x is equal to, halfway between 0 and 3 is 1.5. So b has to be 3 on 2, or 1.5. Alright, so that's b found. Now we need to get our inverse. Okay, so I'm going to say let y equals x squared take away 3x, x equals y squared take 3y. Now, just a little tip with this one here, that the technique we'll use to do this, to get y by itself, will be to complete the square. Alright, so let's do that. Y squared take 3y, halve it, square it, and add it, and then remove it. Alright, so that's going to be x equals y take away 3 on 2, all squared, take away 9 on 4. Alright, so I'm going to do x plus 9 on 4 equals y take 3 on 2, all squared. Let's go over here. Then I'm going to get y take away 3 on 2 equals plus or minus root of x plus 9 on 4. Y equals plus or minus root x plus 9 on 4 plus 3 on 2. Alrighty, now you'll note also that I jumped the gun a little bit with this and didn't write the domain and range of the original function. So let's do that. Domain of f is 3 on 2 to positive infinity. The range of f, the ran f is going to be, so the turning point all the way to positive infinity. So what's the y value of the turning point? To do that, we've just got to drop 3 on 2 into the original function, which is 9 on 4, take away 3, 9 on 2, 9 on 4, take away 18 on 4, negative 9 on 4. Okay, so now what we've got a top half and a bottom half of a root function. Now, which one are we going to take? Well, I know that the range of the inverse is going to be the domain of the original, which is 3 on 2 to positive infinity. That means it's a top half. So we'll say, but range of the inverse is 3 on 2 to positive infinity. Therefore, f negative 1 of x equals x plus 9 on 4 plus 3 on 2, where x is an element. Now the domain of the inverse is the range of the original, so it's going to be negative 9 on 4 to positive infinity. Alright, so I think this is the second last problem. So find the inverse of this and state the points of intersection between f negative 1 or the inverse and the original. Okay, so this one here, you just need to know that to invert that and to write the domain. So I can see that the domain is going to be all real numbers, except you can't throw in a negative 1. What's the range going to be? Well, that's that we need to know what this function is. So the way to do it is to note that when you have a linear over a linear, what you're going to get is a hyperbola. So this is a hyperbola. So I kind of call this one the hidden hyperbola. So to extract it, what we'll do is a bit of long division. X goes into x once. 1 times x is x. 1 times 4 is 4. That's negative 3. So when we did this, our quotient is 1. So f of x is equal to 1. Take away 3, this is the remainder, over x plus 4. So we can see here that the, that's wrong. I've done that the wrong way around. Alright, I'm not going to re-record this because I'm happy to put out the mistakes. Select this stuff here and let's just try that again. X plus 1 goes into x plus 4. That goes into that. 1 x plus 1 gives you 3. So f of x equals 1 plus 3 over x plus 1. So we can see here that the hyperbola goes 1 to the left, so there, x equals negative 1, and 1 up, y equals 1, like so. So we can now quickly write that the range of the original function is all real numbers, except I can't put out a 1. Y can't be 1. Okay, now we're ready to inverse, so we'll go let y equal 1 plus 3 over x plus 1. Swap x and y. X equals 1 plus 3 over y plus 1. x take 1 equals 3 over y plus 1. Multiply and divide. Y plus 1 equals 3 over x take 1. Y equals 3 over x take 1. Take 1. Okay, so f negative 1 of x equals 3 over x take 1, where x is an element of all real numbers, not including, so we can see that you can't use 1, and that makes sense because the range of the original was all reals, not including 1. Okay, so what we've done is find the inverse. Now we've got to state the points of intersection. So the hyperbolas are going to intersect each other twice, if you can imagine it. So here's the line y equals x, and we can see here that we're going to get 2 intersection points. So what we're going to do is we're going to let the inverse, which is 3 over x take 1, equal. Now, we've got a couple of choices. We can let it equal the original, or we can just let the inverse equal x, because remember, one of the first notes we had in this section was that a function will intersect its inverses along the line y equals x. So we can just let it equal x and solve from there. So let's do that. And we can see here that x equals 2 or negative 2. So the coordinates of intersection, we're going to get 2. 2 is one of them, and negative 2 is the other. Now, what about the y value of the intersection? Well, because they always intersect along the line y equals x, that means that the y intersection will be, or the value of y at the intersection point will be the same as x, because it's along the line y equals x. It's going to be 2 and negative 2. We're done. Right, the last problem was one off the 2013 exam. So basically to do this, what I recommend you do is don't do it on the calculator even though it's allowed. So we're noting here that the original function is an exponential function. That means the inverse must be a logarithm. So the inverse of an exponential is a logarithm. Now, what it also means is that this function here, it has an asymptote along the line y equals 3. When we swap x and y, that'll have an asymptote at x equals 3. Alright, so that's important because this can't be the answer, because that's a hyperbola and the inverse of an exponential is a logarithm. This can't be the answer because it has a horizontal asymptote, and this one can't be the answer because the asymptote should be at x equals positive 3, not negative 3. So we're down to B and E. Now the easiest way then to eliminate option B is to note that this coordinate here is when x is 0, y is 2. So the inverse function should have a point at 2, 0. So the x-intercept should be 2, 0. Now notice this x-intercept, I don't know what it exactly is, but I know it's not 2, 0, and it can't be 2, 0 because it's larger than 3. So that's gone. We go to this one here. We can see that we actually don't know what that value is, but it's the only one that can be the answer. So it's got to be E. Alright, when you want to inverse on the CAS, it's fairly easy. You can use this method here, or another method is to go solve. And let's just say that I'm inverting this hyperbola here, solve. So all I do is, instead of typing it in as y equals 1 over 5 take x, actually I'll use the fraction key for this, 1 over 5 take x. All I do is I force it to swap x and y. So I'm just going to rewrite it as x and y. And then all I do is I say solve that for y please, and it will give you the inverse. Right, another cool thing that you can do is actually plot inverses. So if we go to graph and table and plot this function here, if you want, you can actually have a look at what the inverse is by going analysis, sketch, inverse. And we can see here that the inverse of the y equals x squared parabola is the top and bottom half of the root x function. So there it is, all right, 1F and then the inverse functions worksheet.